Dick was good.
I was like, huh?
I almost won like twice. I just couldn't bring it home because I was too intoxicated to do so.
So I was going to give a quiz today.
And you still are.
And what do y'all think? Y'all want a quiz? Next class. All right, I'll give you the weekend, but don't complain on Tuesday. Or wait, sorry, never mind. We don't have the weekend. Don't complain on Thursday that, you know, oh man, it's like a couple of days before Halloween. He's giving us a quiz. So we'll start class with a quiz next time. All right?
Fair warning.
Okay, you're warned. So last class we finished up, we were talking about what?
Shell method.
I started bringing in this idea of the shell method, and I had a couple of students ask me questions after class about the shell method. So I thought I would show you an animation that kind of helps us see, I think, a little better. And I'll ask Vanessa to kill the lights in just a second. Let me just remind you of what the shell method allows us to do. In the shell method, actually, the word comes from the idea of what are called cylindrical shells. Cylindrical shells. So what we do is we take something where, let's say the region that we're trying to wrap around is this region in here. Now I only have one, well, you could look at this as being two functions. There's a function on top and a function on bottom. Here the bottom function is just y equals 0, which is the x-axis. If I wanted to wrap that around the x-axis, I would use washers, right? The method that we learned. And that would be because the rectangle we'd be wrapping around would be perpendicular to the axis of rotation. But if I want to go around the y-axis, what's the trouble that I would have run into here? If I try and wrap this region around the y-axis, what would be the problem? My rectangle would have to be horizontal. And so if I draw that rectangle, the right edge and the left edge come from the same curve. And therefore you can't do like an f minus g if it's the same curve. Because that subtraction should give you 0, and it won't work, right? And there's no way I can rewrite this curve as a function of y to do it sideways. So if all we learned in Cal 1 was the method of washers and, what was it? Washers and discs, right? They're the same thing kind of, but if that was the only method we ever learned, then we could not rotate this around the y-axis, right? Agreed? That's where this comes in. So Vanessa, please. So I hope you can see here. Oh, come on. What's going on here? Okay. Why is this one not moving? Right, so as you can see here, if we look from the side, do you see that blue thing is like the curve I just drew, kind of? If I want to wrap it around the y-axis, what I do is I cut it up into a bunch of rectangles. I still don't know why this thing won't go back. Huh. Interesting. Well, if I take each of these rectangles and get more and more of them, if I wrap them around the y-axis, do you see how they swing around? And I create all these cylinders. Now, they're not coming out towards us. Maybe I can do another one. See if this one works any better. Can't change the angle. I don't know what's going on. Let me try this. Ah, I think that's the problem. There we go. Okay, that's what I was looking for. Okay, you see them? As I wrap these around the y-axis, they swing around like this. So you won't let me do it when I do that. That's what it is. All right, so there they are. Yes, you see them? That's half of them. Imagine they went all the way around. Each one of those vertical rectangles, right? So I wrap it around. Each one would create this cylindrical shell. And what we determined last time is remember we cut that open and laid it flat, and we came up with a formula for this volume wrapped around. Anyone remember what it was? It was 2 pi integral a to b of x times f of x dx. Right? So should I review where this came from, or are you okay with this? All right? I'm about to redo it. I'm going to redo the whole formula for a more complicated scenario than this, but that was kind of what I started talking about with shells. All right? So let's see now if we can adapt this formula to a more complicated region. So let's take a minute to draw two functions that are functions of x but cannot be drawn as functions of y. So how about we do something like this. And then below it, another function here. So I'll call this one g of x. The red one is g of x, and the blue one is f of x. Does everyone agree those are functions of x but not y? Yes? Those are both functions of x but can't be written as functions of y. Mm-hmm. All right. Now, if we want to take this region bounded by those two, and we want to wrap this region around the y-axis like this. Oh, well, you know what? Let's not do y-axis. Let's get more general than that. Let's go around this line over here. What would the equation of that line be? X equals something, right? A number? It could, in this case, x would be negative, right? It would be x equals like -2 or something. But does everyone agree that this would be some number? X is a. So if I go to try and wrap this rectangle around, this one right here, some arbitrary rectangle, then when I wrap it, I get the cylinder, don't I? Let's draw that cylinder. That's what it looks like, right? Does everyone see it on the paper, or like on the page? You know, it comes around like this, goes back, something like that. Right? You'll see that? I just don't want to clutter up my drawing, so here it is. What we did was we cut this open, right? We snipped it, laid it flat, and got the volume of this boxy looking thing. So we needed to know the height. What's the height of this rectangle? It's the top one minus the bottom one, right? The f function minus the g function. That's how tall this is, yeah? So this height is f of x minus g of x. So this is already different than our other formula, because when I did it initially last class, I was only dealing with one function. The bottom was the x-axis. This time we have a different bottom function. Okay, how wide is this little sliver? That's dx, right? Because that came from the width of that piece, dx. And then the length of this thing, we said, was the circumference of that circle, right? When you took it and laid it open, it was the circumference of this was the length of this. So the circumference is always 2 pi times the radius, isn't it? So we need to know the radius, don't we? Yeah, so let's see. This is going to be where things get tricky. Last time we said that the radius was just x, didn't we? That's where that x came from in that formula. But let's think about this. The radius is the distance from the center out to the edge, right? Okay, so that's from this green dotted line out to our rectangle. What we all need to keep in mind is that the distance from the origin to our rectangle is always x. Because we're letting x vary, right? X is going to vary between two numbers, a and b, isn't it? We're going to slide that rectangle back and forth by letting x go from a to b. So this distance from here to the rectangle is x. But the distance from that rectangle to the green is not x, is it? It's actually x plus whatever this distance is also, right? In this particular problem, a would have been a negative number, wouldn't it have been? Would I put like -2 here? No, it's a distance, so what would I put here? The 2, right? Understand? So this is actually going to be, in this problem, I'll put absolute value of a because that will make sure it's positive, right? But I'm looking for a general formula. So what I want you to do is just visualize that the distance from here to the rectangle, we're just going to call it r, all right? Radius. But I'm going to put a little subscript x there to remind you that that radius will always include x in it. X will be in it, but it might be just x, it might be x plus 2, it might be x minus 2. It just depends on the geometry of the problem, the setup. All right? So if this part right here becomes 2 pi and then some radius that's a function of x, then my volume of this is just this times this times this. And then we add them all up, right? Which means we bring in the integral. We go from a to b. We're done. So the volume of that solid of revolution would be 2 pi. That will always come out. A to b. And then instead of me writing x f of x like we did last class, I'm going to put r sub x. That's the radius. And then f of x minus g of x dx. And that's the big daddy formula for cylindrical shells. Any questions on where any of that comes from? Sure? All right, we should do an example. Yeah? Let's do, how about this? The region bounded by y equals x squared minus 1, y equals 1 minus x squared, rotated about x equals 4. Find the volume. So we have two parabolas, don't we? And we're going to take the region bounded by those two parabolas and we're going to wrap it around a vertical line x equals 4. So in the past you thought, okay, if I'm ever going to wrap around a vertical line, you'd think, okay, what I'm going to need to do is write these as functions of y so that I can get my rectangle to be perpendicular to my axis of rotation. But with shells, we don't need it. All right? So I'll start with the drawing. And I'll go quickly through the drawing because I'm hoping you all know how to graph those two. X squared minus 1. This parabola opens up. It's been moved down 1. That's y equals x squared minus 1. Agreed?
Yes.
All right. And then 1 minus x squared is parabola. It's opening down, but it's been moved up 1, and so it's kind of like the reflection of that, isn't it? Over the x-axis. It's this. Our axis of rotation, Vanessa, would you mind turning the light on? I'm sorry to interrupt you. Our axis of rotation is over here at x equals 4. I'm kind of out of room, so I'm just going to put it right here. Is that all right? That's my axis of rotation. Are we all clear on why it is I cannot do horizontal rectangles? We're all clear on that? Okay. Yes? Zach? I didn't hear what you said. All right, so I'm forced to do a vertical rectangle if I'm going to rotate this region, right? So to do that, I'm going to pick some arbitrary rectangle in here, right? In the formula, I need to know a top and a bottom function, don't I? Which I've got. I didn't write the blue one. But I've got the top and bottom, don't I? This one is y equals 1 minus x squared. So that should be, I hate these markers. That should be pretty clear in our formula. Bless you. Let it go. I'm going to write down the formula up here so that we can refer to it. Did I put the dx on the formula? Yes? Okay. I don't remember doing it. All right, so right now we have the f of x and we have the g of x, don't we? The top and the bottom. All right, so the only thing really left for us to find that's going to take some work is the radius, which is the distance from what? Close. Distance from the rectangle to the axis of rotation. All right? So we need to find the distance from the rectangle to the axis of rotation. This is r of x. The one thing we do know is the distance from the origin to the rectangle. The distance from the origin to the rectangle should always be what? That will always be x. Okay, from the origin to the rectangle is always x. So if from here to here is x, and from here to here is 4, then this has to be what? 4 minus x. Right? So if like the distance from here to here, let's say that that was 1, and the whole distance is 4, then this would have to be 3, wouldn't it? It's the same principle. All you're doing is you're taking 4 and subtracting this value. So this r of x must be equal to 4 minus x. Does anybody have a question as to how I got that number, or how I got that expression? All right, so now we're ready. You just plug everything in. We're done. So this is equal to 2 pi. Do you know our limits of integration? A and b here. -1 to 1, right? That's where the two parabolas hit each other. And we're talking about x values, right? Not y values? Because we're integrating with respect to x. So it goes from -1 to 1 just by inspection. Because my graph was pretty good, I'm pretty confident that's where they hit each other. If I wasn't confident, what would I have to do to figure out those values? Set these equal to each other, right? But I can tell it's -1 to 1. The radius, which I write, what, 4 minus x? Think I need that in parentheses? Absolutely, have to have that in parentheses. And then your function of x minus your function f of x minus the g. So f of x was 1 minus x squared minus the bottom function, which was x squared minus 1 dx. Now I kind of have like a lot of parentheses in here, but I'm only doing that to be sure that you distribute that negative properly. All right? So let's clean this up. What does the integrand, what does that inside of that parentheses become? So 2 pi integral -1 to 1, 4 minus x. What is this? Is it just negative? Let's see, 1 minus plus. So we should have 2 minus 2x squared. Is that right? No? This becomes 1 minus x squared plus 1. 1 plus 1, right? So 2 and then -2x squared. And then we would just multiply these out, right? Just FOIL them out. And then you'd have polynomial, and you integrate term by term, and you're there. Okay? Seem easy enough? All right, now let me just, since we have the picture up here, let's do one more problem using the same exact picture. Let's rotate it around a line over here on this side and see how the R of x changes. So how about we repeat the problem, but this time about x is what? What do you want to use? Negative 4? Fine with me. Now what you're never going to face, I would never do this to you, is putting the axis of rotation inside the region. That would cause a problem. All right, so don't worry about that. It's not going to happen. So now, I'm going to come over here and let me draw this. I think I have another color in my bag. Thought I did. I need to go invest in some colorful markers. There we go. It's probably going to look exactly the same as that blue right there. It's a little different. So negative 4. So different problem, same rectangle wrapped around. So we need to know the only thing we really need is the R of x, right? That's the only thing in the problem that's going to change. So distance from the axis of rotation to the rectangle, right? This time would be what? Plus, right? This distance from the origin to here is 4, right? As a magnitude, the distance is 4, and then you have to add the x. So 4 plus x. So all it would do is change that right there to a plus. That would be the only difference in the problem. Understand? Okay. So remember, on your test, I'm not going to be asking you to take every single one of these and evaluate them, right? So what happens if I look at your formula and I said go around x is negative 4, and you have that up there? I mean, you're going to miss a lot of points on that. You can't come back to me and, well, it was just a sign. Well, I'm not asking you to do all the work. The most important thing is this. So if one thing is messed up, that's a big deal. So make sure you get your good drawing and take your time. All right, that's shells. Do we want to see any more of this, or are you okay with this?
Sir, can you go over the R of x when you change it again?
Okay, that thing that we wrapped around, right, this right here, we need to know the distance from the axis of rotation to this edge, because that cylinder comes from wrapping it around that dotted line, doesn't it? Our cylinder is created by this rectangle. So I want to know the distance from here to here, right? Okay, that's what I call R of x. I know that this x value is negative 4, so the distance from here to here is 4, right? That's 4 units, 1, 2, 3, 4. But then the distance from here to my rectangle is always x. So the total distance is the 4 plus the x.
What if you chose your rectangle to be elsewhere then?
Okay. Well, I was wondering if anyone was going to ask me that. It will still work. Okay, so look, do you agree right here with my rectangle chosen this way, the x value is a positive number? Yes? Nope, it's not an absolute value. So check this out. If you just happen to draw your rectangle over here, right? It's going to be a little bit confusing to get this when you try and draw it, or when you try and come up with the formula, because you have to now realize that your rectangle is to the left of the origin, which means your x values are negative, aren't they? So if I'm looking for the distance from here to here, right? You would say, what? This distance is what? 4, right? And then you'd be taking away this x, wouldn't you? But x is negative, isn't it? So what happens when you take away a negative? You add. So you actually would come up with the same exact formula that I come up with my rectangle on the other side. So I'm glad you asked. here's the rule of thumb. Always draw your rectangle making x positive. So that way it's a little easier mentally to deal with. You can, as you can see the way I did that, I had to keep in mind x was negative, and then subtract the negative means adding. So if you don't want to deal with that, just always draw your rectangle on the positive side.
What if you put it in the middle?
In the middle?
Yeah.
Where?
Right in the order.
At 0?
Yeah.
Well, then it would just be 4, wouldn't it? But see, the thing is, your rectangle moves, doesn't it?
Yeah.
You never get to like stop it from moving. That's what the integral does. It adds up an infinite number of them. So if you let x be 0, right? Think about the formula we have here. I'm going to change it to a plus. Think about the formula we have. If x is 0, that would give me this rectangle, right? What's the distance from here to here if x is 0? 4. Okay, what if x is 1? What's the distance from here to here? 5, and that's what I would get here, right? What if x is negative 1? What's the distance from here to here? 3, and that's what I would get here. I don't know if that answers your question. It's variable. X moves. This rectangle is going to float back and forth between negative 1 and 1. We just need a general formula that defines that distance. Our R of x function, no, our range is negative 1 to 1. That's the range that we have on x.
I meant from bound points from end to end.
Yeah, it's going to give you the two ends. When x is a, we should be here, and when x is b, we should be there. Yes?
What if we were to move the whole, both functions in the first quadrant?
Mm-hmm.
How would we do that? Would we do like from 4 to the origin or to this?
You mean if this whole region was over here, right? Then the distance from here to here would be 4, and the distance from here to your rectangle would be x. So you'd still have 4 plus x.
Oh.
We kind of opened Pandora's box there a little bit because you have to be a little bit careful with this rectangle and what its x value is. Because if it's negative and you subtract it, you really are adding. So would you like to see another example, or are you okay? You want to do another one? Okay. I've never really been too satisfied with the problems in the book for this section. So we'll just set this one up. We won't actually do it, okay? We'll set it up and we won't do the integration on it. So what about you have the region? The region is bounded by y equals natural log x, and then y equals e to the x minus 1, and then x is equal to 1, x is equal to 3, and you want to rotate this about x equals 6. So this is the region. This is where you want to rotate it. So let's look at the picture first. Do we all know what natural log of x looks like? Of course, right? Where does it hit the x-axis? At 1. And it goes like this, right? It goes like that. Well, that kind of doesn't grow quite that fast, but is that okay for this purpose? You know what? Let's make this. Might have to bring the e to the x down a little bit. Let's make it e to the x minus 4. Because we all know e to the x looks like this, right? Yeah? I'm just going to bring it down so that it's, we'll what, instead of here, it's 1, 2, 3, 4, so like this. It's gonna go like this. Yeah?
Would there even be a problem if the graphs weren't touching each other?
No, that wouldn't, because I gave you these. Right? So we would have started at 1 and ended at 3.
So there's never anything that says two graphs that just don't touch each other, that's.
Like, they don't have to intersect in order to find the area in between them.
They don't have to intersect to find the area between them as long as someone gives you bounds on the x's.
Yeah.
If I didn't give you bounds and the functions never intersect, there is no region enclosed.
So then,
So it would be a dumb question. It'd be like, you know, I don't know.
a dumb question.
It would be a dumb question. I guess, no, it would be me asking a dumb question of you. You know what I'm saying?
It would just be nonsensical.
That's right. It would be, yeah. Okay, my only concern here is that, that these hit each other before 3. Because I'm supposed to also put what, x equals 1, now that's here, right? And x equals 3, but where's that? So how could I determine if these hit each other before 3 or not? You do what? Plug in 3. Okay, I'm going to plug 3 in. What do I get when I plug 3 into this? It's e to the 3rd power minus 4. What's natural log of 3? Yeah, so look, what's bigger? Natural log of 3 or e to the 3 minus 4? Which one is bigger? E to the 3rd power minus 4 or natural log 3? We'll check on your calculator then. E to the 3 minus 4 is bigger? That means that 3 is over here, isn't it? Because look at my graph. The e function's bigger than the natural log. So 3's got to be over here, can't be in here, right? So don't we have to figure out where they hit each other then? Yes? That's not going to be, I don't think we're going to be able to solve that problem.
So do we just map ourselves into a corner?
Yeah, a little bit, but it's okay. We'll fix it with, we have 2 options. We can either try and get a solution to this and ask Wolfram to do it, or we can move this point over to make it be to the left of this. So what do y'all want to do? Just move the point over and just move that? So what number would work? Does 2 work? Do 2 in here. Do e squared. I better get my calculator out. What's e squared minus 4? 3.4. What's natural log of 3?
0.69.
0.69.
Yeah, that's a log of 2. 0.6.
Oh, we plugged in 2?
0.69.
Okay, so that's not going to work? Got to get closer. We can take off completely, but then don't we need to know that point?
Then we can ask Wolfram.
Set them equal to each other? You want to do that?
Yeah.
All right. We'll take x equals 3 off. So let's solve it. Here, this problem was just supposed to be one more example, and I screwed it up. All right. Let me solve. Can you solve that easily? E to the x minus 4. Uh-oh. My program's having problems solving this. Okay. Let's start over. Let's not move it down. Get a new drawing.
Wait, so Wolfram Math can do it?
My Mathematica couldn't do it, which is Wolfram's brains, so probably not.
Maybe Newton was a quack.
I'll just leave it this way. Just do e to the x natural log x 1 and 3. Natural log x looks like this. That happens at 1. E to the x looks like this, right? X equals 1 is here. X equals 3 is here, yeah? The region's enclosed by those three? Or those four curves? Axis of rotation. I'll give you a second to catch up. While you're doing that, I'll label these things. What was that? I draw my axis of rotation, right? Which is over here at 6. By the way, on your exam, I will not tell you you have to do your volume solids with any particular method. So if you're doing a problem and you think shells is better than the other way, then you're free to do however you want. All right? I won't force you to do one or the other. All right, so here's my rectangle. That rectangle is going to rotate this way. It's going to be parallel to the axis of rotation, which means I'm using shells, right? Shells is always parallel. And so I need to know a top and a bottom function. I've got those. I need to know the distance from the rectangle to the axis of rotation, right? R of x. Which would be what? Six minus x. Because the distance from the origin to my rectangle is always x. And x is positive, right? So, and then the distance from here to here would have to be 6, take away that x. My integral will go from where to where? X value of 1 to the x value of 3. That entire distance was 6. 6, take away that x, and that's this piece right here. Bless you. Okay, I hope that helped a little bit. That one? I mean, it's pretty much the exact same problem that we just did, different functions. So 2 pi integral 1 to 3, that's the bounds on x, 1 to 3. And then I have my r of x, which was 6 minus x. And then the top function, e to the x minus natural log x dx. And you'd have to multiply that all out, wouldn't you? Let's multiply it out, just to see what we'd be looking at here. We get 6e to the x minus 6 natural log x minus xe to the x plus x ln x. I believe that's it. Do you agree with that? Could you integrate each of those? Antiderivative of 6e to the x is 6e to the x. Could you find the antiderivative of natural log of x? That's the derivative. We did it in class once. We used integration by parts. This one is definitely integration by parts, and that one's also integration by parts. It's an interesting problem.
Do you think we do, or there would be a bonus question based on not volume but surface area?
We're going to do surface area today. Yeah. All right, we good? All right, let me move on. We have another type of volume that we want to look at. And I think the best way to motivate the idea is to show you this little animation that I came up with. So, Vanessa, if you don't mind, let's kill the lights. And I don't think I'll put the camera on it. Movie time, yep. Where is it? Here it is. I was messing with the code before class trying to get this to work. This code, look at it, it's pretty nasty, huh? But I got what I wanted, finally. Here it is. Come here. All right, so this is the problem we were just looking at a second ago where we had 1 minus x squared. And we had x squared minus 1. And it created this thing like this, right? That's what we had. And what we did is we took that region bounded by both of them and we wrapped it around some vertical line, right? That is not what we're about to do here, all right? Not at all. So what I want you to imagine is that, and listen to the wording of this. This region is the base of a solid, all right? This right here, the region bounded by those two curves, okay? Those, right? The region bounded by those forms the base of a solid. So above this region is some solid object, okay? Now let me give you some characteristics of this solid object. If you take a cross-section of this solid, does everyone see there's a solid sticking out at us right here? It could be a lot of different shapes, couldn't it? This particular one, if you take a cross-section that runs perpendicular to the x-axis. So I'm going to come in here and slice it like this, okay? Not like this. That would be perpendicular to the y-axis, wouldn't it? A cross-section that is perpendicular to the x-axis forms a rectangle where the base is the distance between these functions and the height of the rectangle is 1. Does everyone see what that is? Probably not, right? I mean, it's kind of hard to see. So that's what this is about. I'm trying to show you this in an animation. So what I'll do is I'll pick an arbitrary slice. That's supposed to be my slice coming through the solid, okay? And when I take a look at that slice from the side, it's supposed to be a rectangle. Does everyone see the rectangle? Where the base of the rectangle is the distance between the functions, and the height of the rectangle is 1. All right, everyone see it? So when I come over here, I don't want to write all the words I just said, where the base is a rectangle and the height is 1. I'm not going to write that all down. What I'm going to do is I'm going to show you how I would draw that here. So I go 3D. We did something like this last class, right? Because Ron was saying, no, it looks like it's going into the board.
Oh, it could go either way.
It could go either way, yeah. So I have a bottom parabola. I'm going to blow this up. A bottom parabola that looks like this. That's not very good. Then I have a top parabola, which goes like this. Okay, that's the thing laying on the ground. And what I did is I came in here with some arbitrary slice, right? And notice I'm picking a slice that's over here on the positive side, okay? That slice creates a rectangle where the height is 1. So from this I go straight up 1 unit, whatever 1 unit is. I lost my slice. There it is. And I get this piece there, right? If I slide this slice somewhere else, the rectangle is going to take a different shape, isn't it? What's going to change? The base, right? The base of the rectangle is going to change. So that's what happens in this animation. I can move, notice the height of the rectangle is always the same. So if I look at it from this point of view, notice the heights across the top are always the same, but the base is getting smaller. So you can see on this little slice at the end, coming from this side, it's very, very small, right? Base. If I take all the infinite slices, put them together, that's the solid. And we want to know the volume of it. So here's me putting everything together. You get that shape. Now notice you can see that rectangle move through the shape. See it? This shape, I want to know the volume of. Understand? All right. So we're going to do it just the way we've done everything else in this class with integrals. We find a formula for what it is we're trying to add an infinite number of these things up, right? If it's area, we found the little rectangle formula, and we did an integral on that formula. If it's a volume, we created washers, we added them up. If it was the shells, we did the shell formula, we added them up, right? So let's just figure out what the volume of one of these little cross-section slices is. So I need to add a little bit of width to this, right? How do I add width to the little slice? I make it how wide? dx, right? Which over here would create a little bit of width to this and give me like this little slab, wouldn't it? That little slab now has width to it, it's dx. So let's take that picture over here and figure out the volume of just that one slice. So I'm going to kind of draw it over here. We know this is what? dx. Do we know this?
1.
It's 1 because I told you in the problem the rectangle always has a height of 1. That's never changing. The only thing that changes is this piece right here, right? That varies. That actually depends on where we are, doesn't it? And according to our formula, I'm sorry, our picture, it's this distance here, isn't it? Which is, how did we always find the distance? We had a top and a bottom. F of x minus g of x, right? What's the f of x for us here? What's the top function? 1 minus x squared. What's the bottom function? X squared minus 1. So this distance from here to here should be the f function minus the g function. So what is f take away g? F take away g. Let's just do the algebra there. Didn't we do that earlier? Isn't it 2 minus 2x squared? That right there is this. Agreed? That's the dimensions of this little sliver. Now we multiply those three together, right? And that gives us the volume of that little sliver. So what's the volume of the entire thing then? Of everything, the whole solid. How do I do it? Integral, right? Because I'm going to add up all these slivers. From -1 to 1 because I'm going to be integrating with respect to x, right? And I can tell from my picture x goes from -1 to 1. 2 minus 2x squared dx times 1, but I don't really need it, do I? So you see this formula, that's it. There's nothing more to do. There's no 2 pi in there. There's no pi, r squared. We're not doing washer. We're not doing a disk. We're not doing a shell. We're coming up with a formula for one slice, and we're adding them all up. That would be pretty easy to evaluate, wouldn't it? Any questions? Let's try something else. Let's do the same exact region, all right? Same exact region. This time, I'm going to tell you that when you do a cross section, right, like this, do a cross section, that it forms a square. That's it. Forms a square. So what's the difference? Let me draw that a little bit bigger.
It's not they're not curved, they're just straight lines.
Okay, so like on the one we had right here, didn't we say that those heights were always the same?
Yeah.
Right? Because it was a rectangle, it was always 1. This time, the heights are going to get smaller as we move further out because the base is getting smaller. If they're squares, the base and the height are the same. So let's see if we can get our heads around what this thing's going to look like.
Would it be f of x minus g of x equals 1? Would you equal it or set it equal to 1?
No, you don't need it.
That's what I was thinking.
Look, those are all squares, right? Notice how the base is getting smaller as I move out to the edge. But if it's a square, that means the height has to get smaller. And so I get down to almost a little point where it pinches off there, right? In the middle, it's the biggest it will ever be, right? And then on the other side, it does the same thing. It shrinks down. So let's take a look at that one. That's the shape. Very different than this shape, right? That's rectangle above. This is a square above. Got it? Okay. So we have the same two functions like this. The reason I'm writing it all down here, up here, is because, again, I want you to see, like on a test, how you would, like, what is the work I'm looking for? Well, I'd want you to do this. I want you to label these graphs, y equals 1 minus x squared. This one here, y equals x squared minus 1. You would show me a typical slice on this thing, right? Your slice comes through. Go ahead and lay that slice on the ground. Is that what it would look like? Notice I'm not even drawing the axes anymore. I'm just laying that slice on the ground. What shape does it form with that slice? We said a square, right? So however long this is how tall it is. So I've got to go up, over, down, something like that. But it's a square. How wide is this thing? Dx. How about that piece? That's f minus g again, isn't it? Which for us, we've already done this. It's what? 2 minus 2x squared. But since it's a square, that's what the height is also, right? So this is 2 minus 2x squared. So what's the volume of this one slab? This times this times this, right? Add them up forever, infinite number of them. So our formula is just going to change a little bit, isn't it? Just a little bit. Formula is going to be integral negative 1 to 1. It'll be 2 minus 2x squared squared dx. Does that mean you could have just found the answer to the other one and squared that answer? And careful, yeah. If you just do the other one and then square the answer, it's different than this one, because this one you have to integrate the thing that's squared first, and that would be much different. You can check it yourself, but I guess what I was just asking you is this. This is more of an abstract idea. Is this true? In general, is this true? Take the integral of a function from a to b. Take that numerical answer and square it. Is that equal to, question mark, the integral from a to b of the function squared? No, it's not. This is the area under the function, right? F. Whatever that area is, if we square it, is that equal to the function squared area underneath? No, not in general. All right, we're going to keep moving. What if what I said was these cross sections formed circles? And the circles have as its diameter the base of the region. So same picture. But this time the cross-section forms circles where the diameter is the base of the region. So take this slice that is perpendicular to the x-axis, lay it down on the ground, and what you know is that this is the diameter of a circle that is formed. So can you draw a circle like this? And then give it some thickness like that. Do y'all see it? It's like a disc, isn't it? But we're not going to use the method of discs. We're just going to come up with a formula for that. Right? Mm-hmm. But it is a cylinder, and we do know how to find the volume of a cylinder, don't we? The volume of a cylinder is pi r squared h. Do we know the height of this cylinder? The thickness of the cylinder? Dx. The only other thing we have to resolve is what? Pi r squared h. So we need what r is, right? We need the radius. The radius is the distance from here to the edge, isn't it? Is that f minus g? It's half of f minus g, isn't it? F minus g is the whole thing, right? You want halfway. Could I have just used, instead of saying half of f minus g, could I have just used f?
On this one.
On this one only because it's symmetric, but in general, no. This one you could have, but in general, f and g don't have to be mirror images of each other. So this distance will be half of the f function minus the g function. Do you agree? Yeah? Everyone's okay with that? Mm-hmm. Which for us, in this particular problem, we had already done f minus g several times. It was 2 minus 2x squared. So for us, this is just 1 minus x squared. Yeah. Half, half. So what is the volume of this sliver here? It's pi, right? Pi times this squared times the height. And then we need to add them all up. So my integral. The volume would be integral -1 to 1. Pi times, I'll bring the pi out, 1 minus x squared, squared, right? So it was pi r squared times height. Then you multiply that out, integrate, you're done. Last one. Oh, I never showed it to you. Circles. So there's a circle moving through, and there's the solid. Right? We can find the volume of that. What if I said instead of circles that they were semicircles? It would be half of this, right? And that would work this way. You would just take half that volume if they were semicircles. So if they were semi, all you do is just put a half in front of this. All right? Last one. Last one. Same region. Cross sections that are perpendicular to the x-axis form equilateral triangles where the side, the base of the triangle is the distance between the two functions. Equilateral, y'all know what equilateral means, right? All sides same length. So, getting tired of drawing this picture. I think you're probably getting tired of seeing it. Here's my region, my little rectangle that I'm going to lay down over here. Lay down. This isn't going to hurt. Well, at least you're paying attention. Ron, I wasn't sure if you were there, but you are. Okay. There we go. Equilateral triangle. So like this. Right? All the sides are the same. So just like everything else, we just need to come up with, a way to find the volume of that. We know this, right? We know this is dx. What we need now is the area, don't we? The area of the face of this, whatever the area of the face of this is, times dx is the volume. So what's the area of that triangle? And I heard Zach said that this right here we know is what? 2 minus 2x squared. We've got that? All of them are the same, aren't they? But what's the area? 1/2 base times height. Do you know the height? All the sides are the same, but that doesn't tell you anything about the height. Is it 1? It moves. The triangle's changing, right? Remember this. Here's your triangle. Right? As you move it around, the triangle gets smaller. Right? Is it half of that? I don't know. Let's be safe. Let's make sure we all understand how an equilateral triangle like this would work. This is 2 minus 2x squared. I'm looking at this just straight on. Everyone in here said that the area of this was what? Half of base times height? The base in this problem is 2 minus 2x squared. The height is right here. So I want some ideas here on how I'm going to figure out what that height is. Take half of what? Half of this would be from here to here. Do you all agree we could do that? So you're just telling me to look at half of it then, right? That's half of it. This is h. Now what?
2 minus 2x squared is the hypotenuse.
The hypotenuse is the actual other length, so that's 2 minus 2x squared. And then what? Pythagorean, right? This squared plus this squared is this squared. No, this squared plus this squared is this squared. Right? You are paying attention, Ron. All right, so we could do that, right? We could, and we would actually have an equation that has h in it and x. We could solve for h and replace that h with that equation of x. Too hard. Too much work. Okay, so I'm going to remind you of something here. This is important because it's come up in calculus before, so I want to make sure you're aware of it now, okay? Go back to this picture. We knew that all sides were the same, right? We have the classic formula for the area of a triangle, area equals 1/2 base times height. But we have another one. And I know for a fact I told you what it was. It was very early in this class.
The one with sine?
It was the one with sine. 1/2 AB sine theta. This is the formula for the area of a triangle if you know two sides and the angle between them. This is the formula we would use. Because it's equilateral, what does theta have to be? 60 degrees. And what is sine of 60 degrees? Root 3 over 2. Root 3 over 2. So that means this formula becomes 1/2 a times b times root 3 over 2, which is root 3 over 4, just putting this and this together. And then look, if a and b are the same, right, on an equilateral triangle, this becomes, what, like b squared? I could have said a squared, but. This is a general formula for any triangle. This is actually the formula for the area of an equilateral triangle. Because equilateral will always have 60 degrees. You'll always get this formula, and A will always be B if they're equilateral, right? So that is actually a formula we can use. So what's the area of this triangle, everyone? Root 3 over 4 times 2 minus 2x squared squared. Now, if you were to do it the other way with that right triangle and do it and solve and put, you will get the exact same expression. But it's much less work if we remember this. Okay? So back to that little slab thing we had. What's the volume of that thing going to be? That times dx. That's it, right? We just need to throw that little width in there, dx. So we want to integrate now, right? Integrate, negative 1 to 1. That with a dx tacked on, and we're there. Y'all okay? Feels like Monday. I'm going to pull root 3 over 4 out because it's a constant. 2 minus 2x squared dx. That would be the volume of that shape. We didn't look at the shape. It's cool looking though. Whatever the heck that is. I like that. Looks like you could hurt someone with that, right? Like a hat. My poor internet students have no idea what I'm talking about. All these files are available to my internet students, so see if any of them ask me for it. What do y'all think? Going to have a problem like this on tests for sure, all right? I'm going to give you a region. I'm going to tell you what perpendicular. Help me with the wording on this one. This one we just did. I would say, you know, a region is bounded by y equals 1 minus x squared and x squared minus 1. Cross sections perpendicular to the x-axis form equilateral triangles. All right? In the wording, it should all be there. I think I'm ready to move on. Did I give you a homework assignment out of here? I did, right? But I didn't give you the full assignment. So what did I say on 7.2? 1 through 11? So you should probably do in page 379. I already gave you 1 through 11. I believe I want you to go through. You should probably go through 19. 1 through 19 odds. I think that's what I did on my videos. I think I did 1 through 19 odd. But then you should also do like 39, 40, and for the shells section, which is page 385, I would just look at (9) through 13 odds. So I was thinking about this while we were drawing this equilateral triangle. I was saying, hey, you know, equilateral triangle, all the angles have to be the same. So I said, you know, what's this angle? Everyone said 60 degrees. Are you raising your hand?
Yeah.
Yes. What's?
Do we have notes for this online? For the section, like, so we can read the wording and
I do not have notes on this, but I do check to see online to see if I have old tests. My old tests will have the wording, and that way you can go look. If you can't find something, let me know. I'll put something up there. I said, okay, yeah, 60 degrees, and everyone said they agreed, right? Why?
180 degrees.
Some of the angles of a triangle is 180 degrees, right? Not always, right? Not always. So I'm just going to show you this real quick. We all know triangles, and we're usually, well, when we work with triangles, we're in two-dimensional space, right? On a flat sheet of paper. And the rules on a flat sheet of paper are that if you draw a triangle on a flat sheet of paper, the sum of the angles must be 180. We all agree on that? That's called Euclidean, two-dimensional Euclidean space. But if you go to what's called spherical space or spherical geometry, where instead of living on a flat sheet of paper, you live on a sphere. And what I mean by that is the surface of the sphere is your space. You cannot go off the surface. You can't go into the center of the surface. You live on the surface, all right? That's called spherical geometry or spherical space. If you're on a spherical space, then you look at what a triangle is on a sphere. So take, let's say, the North Pole. If you go down to the equator from the North Pole, you would go in a straight line, right? Well, you would walk straight down to the equator. But because you're on a sphere, you have to walk on the curvature of the sphere, don't you? So you'd go like this, and you would walk down. You'd go down to the equator like that. For you, it would appear to be a straight line because you're just walking straight, yes? But we know it's curved. And then on this side, from here to here, let's go to the equator over here. We get another point. And if we walk along the equator, we connect these. So on that sphere, that's a triangle. It's 3 points connected. That's what this was. 3 points connected within the space, right? That's 3 points connected within the space. The angle between these two right here, imagine like a tangent line, right, running along that curve. And then imagine a tangent line running along that curve. When they come together, they're going to come together at 90 degrees, aren't they? So this is going to form a right angle right there between those two. And so is this. But you have another one up there, which this one, that could vary because I can make it very narrow, I could have walked like this. Just do a real small little slice like that. I don't know if y'all can see that. That's not a good one. Let me go like this. That's supposed to be like a slice into the sphere. You see it? Okay, so this angle up here is, well, doesn't have to be 90 is what I'm saying. But the problem is we've already used up, what, 90 and 90? We're already at 180, aren't we? And then we have another one up there. So when you say that the sum of the angles of a triangle have to be 180, the real thing that should be asked after that is, well, what space are you in? If you're in two-dimensional space, yes, I agree, but if you're in some other space, that doesn't have to be the case. Just a little FYI. For those of you doing more math, that comes from a class called non-Euclidean geometry. Sounds annoying. Well, I said that's Euclidean geometry, two-dimensional space. It's non-Euclidean geometry is the class. So everything not that. It's cool. It's a cool class. Yeah, it still sounds annoying, but all right, we're going to move into 7.4, and we're going to do 7.5. We're going to knock it out in the next 25 minutes because I'm not going to do a complete full treatment of these two sections. A lot of instructors actually don't dedicate a lot of time to this, but I think it's worth looking at, all right? So please, with an asterisk next to this, that I'm not giving you the full treatment here, okay? It's just going to focus on functions of x, only functions of x, and that's it. I'm not going to be worried about functions of y, right? Just functions of x. If you want to get in, change it where they're functions of y, then you have to look into this section a little bit deeper on your own. But I will only test you on something like this, all right? So 7.4 is called arc length, and 7.5 is called surface area, and they're very much connected. So let's start with arc length. If I have this curve, and I take this curve off the sheet of paper, and I straighten it out like it's a string, and I put the two ends here, I would like to know what this length is, L. That curve taken and stretched out. Yes? Understand? So the way I'm going to do this is just like I did before. I'm going to try and approximate a little tiny infinitesimal length and then add all those little infinitesimal lengths together to get the total length. Just like when we wanted to find the total area, we looked at an infinitesimal area and then added up all the infinitesimal areas, right? So let's zoom in, okay? You like zooming in? Let's zoom in. I'm going to zoom in right there, this really little, tiny little infinitesimal little piece of that curve. Here it's zoomed in. Here it is. All right. I have this little piece of the curve right there, right? Zoomed into it. I have two endpoints to that little piece, don't I? I can approximate the length of this curve with a straight line. Do you agree that that blue straight line is approximately equal to that curve? How could I get a better approximation? Go even finer, right? Even smaller piece. But see, I'm going to get to that because I'm going to use an integral, and the integral is going to let me cut this up into an infinite number of pieces, right? So what I'm going to do now is figure out if I can get a grip, a measurable quantity for that blue piece. So I'm going to create a right triangle. Doesn't that seem pretty natural? How wide do you think this is? What do you think the distance from this to this will be? We want it to be what? Infinitesimally, and what did we use for infinitesimally wide thing? dx, right? Isn't that what we used for dx? Yes? This is dx. And the slope of this line should be approximately the derivative, shouldn't it? Cal 1, the derivative is y prime. And that means rise over run, slope, should be the derivative. That means that this side has to be dy, the infinitesimal change in y. So that if I take dy over dx, rise over run, I get y prime. Isn't dy dx y prime? Isn't it? And that should be the slope of the tangent line. Y'all following me? With that, can you tell me what this little length, I'm going to call it little l, not capital L. Capital L is the whole thing I want, right? This little l right there. I don't write in cursive often, but there's cursive L. How are you going to get little l? What now? No, just give me a way of determining L from what we have, the other parts of that picture. Yeah, it's just Pythagorean, right? Pythagorean. I could set up a relationship between these. It would read as follows. dx squared plus, dy squared equals L squared. Yeah, that's a relationship. And I could solve for L by taking the square root of both sides. So little l would be equal to square root of dx squared plus dy squared. Yeah? I'm only going to take the positive because L is a length, right? So I don't take the negative root. Now, what we've done in the past is once we've determined a value for this, haven't we brought in the integral? Right? And we added these up. We're going to run into a little bit of a problem here. Remember, this was the zoom in, right? This was the zoom in. Here was the graph originally. We zoomed into this little piece. This x value where we started and stopped will be a and b, right? So we do know our integral should go between a and b. But what's the problem with the integral that I have right now? Does anyone see what the problem is? It should go from a to b. What's that? Yeah, it has x and y in it, doesn't it? I mean, look, this is, if this is what belongs in here, what the heck is that? Right? I mean, like, what the hell is this thing? Remember, all I have is some function of x here, right? Some function of x. I'm trying to figure out the length of it. Oh, so I'm supposed to take the square root of dx squared plus dy squared. And notice I don't even have out here dx. Like I don't have that differential out here that tells us with respect to what variable. It doesn't even appear here. So does this kind of look like something we have not seen? Okay, it should not look familiar at all to you. So I'm going to help us force something nice out of that. Here it comes. Recall the definition of the derivative of f, which we also called y prime, right? When we said y was equal to f of x, f prime of x was equal to y prime. But there was another notation, dy dx. Yeah? Okay. Look at these two right here. If I multiply, and I know there's some things, any real math major that would be watching this video would understand that I'm kind of breaking the rules here, but for a class like this is okay, all right? We're going to multiply both sides by dx, essentially here. And we get y prime dx equals dy. This is the way the book explains it too, so I'm not really like straying away from what people normally do to explain this. But I need a little disclaimer, sorry. Y'all kind of buy that? You buy this? I can replace dy with this. So I would like us to go back up to that expression. I'd like us to replace the dy with that. So integral a to b square root dx squared plus y prime dx squared, right? And this is multiplication right here. What can I do inside that root? Anyone see it?
Pull out a dx.
Pull out a dx out of the entire root, right? This has a dx squared. This one has a dx squared also, once I square it. They both have dx squared. I can factor it out and then pull that out of the entire root as a dx. So what's still in the root if I pull out a dx squared? 1 plus y prime. And the dx came out, so I'm going to slap it to the back.
Oh, isn't it y prime squared?
Y prime squared, thank you. Y prime squared. So this part right here, I didn't show this, but this was y prime squared times dx squared. And then since these both have dx squared, we pull it out and then pull out square root of dx squared is just dx. Does that look like something you can handle now? If you want to know the length of this arc, if you want to know the length of this curve of the function of x between a and b, then you must be able to do what? Take the antiderivative of the square root of 1 plus the derivative of the function squared. And that will give you the length of that arc. What do y'all think? That okay? It's a formula. Now we need to apply it. Y'all want to do an example? Absolutely. Now I did these the videos for this homework set already. So these are all out there, and the next section is also out on the web. So I've got everything through the end of chapter 7 is out there. All right, so let's find the length. Find the length of y equals x squared minus 1/8 natural log of x from x equals 1 to x equals 2. Keeping in mind here the entire time that if we're going to find the length of a curve, I must be able to integrate this, right? I have to be able to integrate that. Which means that, I mean, we already know how complicated things can get with square roots, right? And things being squared. So if I just pick a function out of the air, the chances that I'm going to be able to integrate it are pretty slim. So when you do these problems in the book, they pick these functions very carefully so that when you do take the derivative and you do square it and you do add 1 and take the square root, it's something doable. So let's see that looks like a weird function, doesn't it? Let's see what happens when we try and get it into there. So we're going to need for this the derivative, right? We're going to need to square the derivative, and we're also going to need to add 1 to it and then take the square root. So why don't we start this problem by taking y prime, which is 2x minus 1 over 8x. Derivative of x squared is 2x minus 1/8. Derivative natural log of x is 1 over x. There it is. Now what you need to do is square it, right? So I'm doing this piece by piece. I'm kind of gathering the things I need to plug in here. The derivative squared would be 2x minus 1 over 8x times 2x minus 1 over 8x. This is just algebra now, right? What is that? 4x squared. What do you get in the middle? What's this times this? It's 2x over 8x, which is 1/4, and then subtracting it. So minus 1/4. And then what do you get in the other middle multiplication? Another minus 1/4. The x's cancel there when you do this multiplication. So minus 1/4. And then the last one, positive 1 over 64x squared. You multiply 1 times 1, you multiply 8x times 8x, get that. This is going to look nasty, okay? It's going to look bad, but things are going to be nice in the end. Because again, they're very careful to pick something that's going to work. We good? Is that the derivative squared? Yes? Okay. Now we're supposed to take that and do what? Add 1. Right? Add 1. So I think I'm ready to write the integral down at this point. I'm going to go ahead and set up the whole integral. My integral will go from, what, 1 to 2? Right? Because they said from 1 to 2, x equals 1 to x equals 2. And then it's going to be the square root of 1 plus this thing, 4x squared minus a half plus 1 over 64x squared dx. Any questions?
terms, the x squared?
You can combine the 1 minus the half. You can't combine these together because they're not. One's on top, one's on the bottom. So the most I could do at this point, I guess, would be 1 to 2 integral, what, like 1/2 plus 4x squared plus 1 over 64x squared. What? What?
They could take it out of the square root.
Do what?
You can take them out of the square root,
Take what out?
the x squared.
Well, this one doesn't have an x squared. If I'm going to factor an x squared, I have to have x squared in all of them. I don't know if that's what you meant.
Distribute. No, never mind. You can't do that. It's not multiplication.
This looks like a really bad integral, right? I mean, it really does kind of look bad. But I'm telling you, again, they picked the problem so it would work. So there's some more algebra we can do here.
Power?
What's that?
We can power.
Not because square root, we can't. If there were no square root here, we would just do power rule, we'd be done. But the square root screws everything up. So let's do this. This right here, I'm going to work with this on the side. 1/2 plus 4x squared over 1 plus 1 over 64x squared. What am I about to do? Get a common denominator. All right? So my common denominator will be 64x squared. That means I have to multiply this top and bottom by 32x squared, top and bottom. And that will create the 64x squared on the bottom. What do I have to multiply top and bottom here? 64x squared. What's 64 times 4? 256, x to the 4th, and then finally, I don't have to touch that one, right? Now I can put them all together. On the top, let's put that in descending order. My new numerator, let's put it in descending order. Highest power of x down. Would it not become 256x to the 4th plus 32x squared plus 1, and then the bottom 64x squared? Isn't that what it would become? Now, again, they picked this problem so it would work. The top is a perfect square trinomial. Anyone see it? It's something times itself. What is it? 16x squared plus 1. This right here is 16x squared plus 1 squared. If I square that, don't I get this? 16 times 16, 256. 16 plus 16, 32, and then the 1 at the end. So verify it on your own, but be ready for that on a problem. I mean, these got to work out. The algebra's got to happen, right? All over 64x squared. But what does this whole thing live under over here? A square root. And that, I'm going to like that, because if all of this can be rewritten as 16x plus 1, x squared plus 1 squared over 64x squared, then I can take the square root of each one, right? Separately. And when you take the square root of something squared, it goes away. And the square root of the bottom is easy, 8x. So you get what? 16x squared plus 1 over 8x dx. What could you do there? Two different fractions, right? This over this over this. And you're there at that point. It's 2x plus 1 over 8x, and then you can integrate that. Dot, dot, dot. You can take that the rest of the way? You think? I have 5 minutes. I guess I'm out of time. Well, no, I have 6 minutes. I know you want to go. I know. But I'm more curious than anything else because I was going to start this arc length problem with the following, and I wanted to see if it would interest you at all. What is the circumference of a circle? 2 pi r, right? That's what you've been told? Couldn't I verify that by trying to figure out the length of that blue piece and then multiplying it times 4? All right, so that means I would have to write this blue thing as a function of x. So assuming that this is a circle with radius r, we did this before, didn't we? We said that that is this. Circle centered at the origin, radius r. You don't need to write this down necessarily. This is more of just an exercise. And I could solve for y, and I get this. We did this when we verified the volume of a ball, right? It was 4/3 pi r cubed. I did the same setup. But this time, I'm trying to find the arc length. So I'm going to need to take the derivative of this and square it. Right? What's the derivative of this? Uh-oh, well, derivative root of something is 1/2 times the root of that something, right? Times the derivative of what's in here. Careful, r is a constant. Right, derivative of r squared, 0. Negative 2x. That's the derivative. Clean that up. Negative x over root r squared minus x squared, yeah? What's wrong? Yeah, those twos went away. Then I'm supposed to square this, right? Hold on, I haven't even gone into the arc length formula yet. Square this, which would give me x squared over r squared minus x squared. That's nice, right? Squaring that, the negative goes away. Squaring the root goes away. Wonderful. Now I'm ready for the formula. My integral should go from where to where? 0 to r square root of 1 plus y prime squared. This, right? Oh, sorry, this one, right? Which is x squared over r squared minus x squared. Starting to get excited. What should I do now? What should I do now? What worked last time when we looked at it and said, what the hell do we do? What worked? Common denominator? When we get a common denominator here, you're going to get on top and bottom here r squared minus x squared. And so when you do the addition, I think the x squareds cancel. And you're just left with r squared on top, and on the bottom, r squared minus x squared dx. Right? Can I split this into 2 roots? Root on top, root on bottom? Yes? What's the square root of r on top? Sorry, square root of r squared. R, that's a constant. Pop it out. R. What's still left? 1 over square root r squared minus x squared dx. How would you do that integral? Trig sub. Right? R is a constant. But we probably have a formula for this, don't we? Let's go to the formula. What formula is this? Is it on our sheet somewhere? It's formula number 16. It's formula 16. So we have r from the front. Formula 16 says arc sine of u over a, where u is the variable. So for us, u is x and a is r. So this should be x over r. And that's it, right? That's the antiderivative. Evaluated where to where? 0 to r. Plug r in. R over r? 1. Arc sine of 1?
No.
Pi over 2. So we get r times arc sine of 1, which is pi over 2. minus now, plug in 0, arc sine of 0 is 0, who cares? So our answer is pi over 2 times r. But that's only the first piece. Times 4, 2 pi r. Time to go. All right. Homework for this section, how about get caught up? All right? I will see you for a quiz on Thursday. So be on time Thursday, because I'm going to start class with the quiz right away. I don't want people coming in 10 minutes late. Watch, I'm going to be late now, right? I'm going to be the one who's late. No class tomorrow. Campus.